Welcome back to the deep dive. Anyone navigating just the sheer volume of information that hits us every day? News feeds, product reviews, research papers, the challenge, right? How do we make sense of all this vast, intricate data? Especially when it's not neat and tidy numbers, but complex things like images, like text. Well, today we're plunging into exactly that. How we transform this kind of rich, unstructured data to make, well, powerful predictions and maybe even understand cause and effect better. Our focus for this deep dive is feature engineering for causal and predictive inference. We're drawing really heavily from a very recent March 2025 chapter by Viktor Chernozikov and his colleagues. Some great stuff in there. So our mission today really is to uncover this fascinating world of embeddings. You can sort of think of it as machine learning and AI converting all that rich, messy, unstructured data, sprawling product descriptions, detailed images into usable, low-dimensional numerical features.
It's almost like getting a super efficient information-packed summary of a massive book, but one specifically designed for machines to, understand and act upon.
Precisely.
Yeah, traditional statistical models, they often demand data be perfectly numeric, right? But the real world, it's just awash in complex, unstructured information. So the fundamental problem is how do we extract meaningful signals from this rich data and actually make it actionable for analysis? And think about a really compelling real-world example, predicting product prices. What we often call hedonic prices. Imagine you're trying to price an item using, say, only the text description and the images you'd find on a web page. The real challenge there is transforming those complex inputs into these numerical embeddings so that, similar products end up yielding similar price predictions. That's the magic we're after.
Okay, so let's unpack that. What are these embeddings we're talking about? Why are they suddenly so pivotal?
Right, so at their core, embeddings, or you might hear them called encodings, they are basically relatively low-dimensional numerical features or summaries derived from complex objects like text or images. The baseline requirement is pretty intuitive. Similar products should give you similar embeddings.
Which, in turn, makes sure that your price predictions for similar items are also similar. Makes sense. But the more ambitious goal, and honestly the more powerful one, is for these embeddings to efficiently approximate as much information, as much of the useful signal from the original text and images as possible, especially what's relevant for prediction.
And how do we actually make these smart summaries? The sources seem to point to three main paths, right? There's the classic principal component analysis, PCA, then autoencoders, and then these neural networks that solve auxiliary prediction tasks.
Exactly. That concept of auxiliary tasks is really quite clever. These aren't the final prediction task you care about, like, say, predicting the price. Instead, they're related problems that essentially pre-train a neural network to learn incredibly useful representations of the data.
Oh.
So, for instance, with images, an auxiliary task might be classifying the object in the image. Is it a shirt? Is it a car? For text, it could be something like summarization or maybe even machine translation. So what we do is we use networks that have gotten really good at these other tasks, these auxiliary tasks, and then we basically just extract the intermediate features. Those are our embeddings.
Got it.
And those are what we feed into our main prediction problem. So think about using a powerful image classifier like, say, ResNet50 to create image embeddings, or a big language model like BERT for text embeddings. You're kind of leveraging this general understanding the model already has.
That makes sense. Let's trace this evolution then. It sounds fascinating. From these classical roots up to cutting-edge AI. Where did this idea of embeddings really start?
Well, you mentioned PCA, principal component analysis. In many ways, that was kind of the original embedding technique. It showed us how you could take high-dimensional data and distill it down into a much smaller set of principal components that still captured, most of the original variability. It's basically finding the key directions in your data that best reproduce it. You can almost think of PCA as a sort of linear autoencoder.
A linear autoencoder? How so?
Well, it encodes information into a lower dimension, the principal components, and then it decodes it implicitly to approximate the original data just using linear combinations. So its insights really laid the groundwork for thinking about creating efficient summaries.
Okay, so PCA gave us a powerful linear way to summarize. But like you said, the real world is rarely that simple, rarely linear. How did autoencoders take that idea and run with it, moving beyond linearity?
Yeah, that's exactly where autoencoders come in. They're essentially a neural network-based generalization of PCA, much more flexible. Their main goal is to discover these latent or sort of hidden low-dimensional structures within a data set, and they work by minimizing what's called reconstruction loss. Basically, they try to reconstruct the original input data as accurately as possible, but after compressing it down into a low-dimensional representation, like a bottleneck layer.
Right, compressing and then expanding again.
Exactly. And unlike PCA, autoencoders can use nonlinear functions and multiple hidden layers. This lets them find much more sophisticated, more nuanced representations in the data. And we should probably mention variational autoencoders, VAEs, too. They're an important extension that adds a bit of randomness, stochasticity into the encoding. This allows them to learn probabilistic mappings, which can be really useful.
Okay, so autoencoders focus on reconstruction. But you also mentioned general embeddings using these auxiliary tasks. How do they take it even further? It sounds like they're not just trying to copy the input anymore.
That's the key difference, yeah. General embeddings are a generalization of autoencoders. Here, you train a network using other loss functions. The target outcome, let's call it A, isn't necessarily the original input W. So for example, instead of an autoencoder trying to reconstruct an entire product image, we might train a network where the auxiliary task is just to classify the type of product in the image. Now, the embeddings you get from that task might actually be far more useful for your main goal, like predicting the product's price, because they're already optimized for something meaningful and related to the product's characteristics.
Ah, I see. So you leverage a related task to get features that are more relevant to your ultimate goal.
Precisely. It's about using pre-existing knowledge that's sort of embedded in these powerful models trained on other, often massive data sets.
All right, let's dive into text then. This is one of the trickiest types of data, right? Human language. So messy, so nuanced. How do we turn that into something computers can actually work with effectively?
Yeah, text is a challenge. The first sort of big breakthrough in modern embeddings for text was probably Word2Vec, around, 2013. The problem before that was simple encodings, like, giving each word a unique ID and a huge vector. Didn't capture any similarity. Cat and kitten were just as different as cat and car.
Right, no semantic understanding.
Exactly. Word2Vec's genius was to represent words as much lower dimensional vectors, maybe in a few hundred dimensions instead of millions, where the position in that vector space captured semantic similarity. Words with similar meanings ended up close together. It learned these embeddings, basically, by predicting a word from its surrounding context words. The paper gives an example like, Haigu fashion women's multi-pocket cotton canvas handbags.
Okay.
The model might learn by predicting fashion when it's given Haigu and women's as the context, and the results were pretty amazing. Very similar words like shirt and shirts have almost identical embeddings. Luggage and dress are far apart. But the really mind-blowing thing was these vector space analogies. You would take the vector for men's, add the vector for handbags, subtract the vector for women's, and the resulting vector was remarkably close to the vector for briefcase.
Wow. That's incredible. It learned relationships.
It really did. And that gave strong justification for doing things like averaging word embeddings to get a representation for a whole sentence or document. Although it's important to add a cautionary note here. These embeddings can unintentionally pick up and even amplify societal biases present in the training data. Things like gender stereotypes, that's something you always need to be aware of.
That's a really crucial point.
Yeah.
Okay, so Word2Vec handled words and their similarities, but language flows, right? It's a sequence.
Yeah.
What was the next big step? You mentioned ELMo. How did that improve things?
Right. ELMo, which stands for embeddings from language models, was a major step forward because it explicitly treated text as a sequence using recurrent models. This was huge for capturing context.
Context being key.
Absolutely, because a word's meaning can change dramatically depending on the words around it, right? Think about the word bank, river bank, financial bank. ELMo used what's called a Shannon game approach, essentially predicting words based on the words that came before them or the words that came after them. It relied heavily on recurrent neural networks, specifically LSTM's long short-term memory networks.
LSTMs, right? Good for sequences.
Exactly. They're particularly good at handling sort of long-term memory or dependencies across longer stretches of text. So ELMo would run through the text forwards and backwards predicting words. The final embedding for a word wasn't fixed like in Word2Vec. It was a function of the entire context, derived from a weighted average of the hidden neuron outputs from the LSTM. So it became much more context-aware, typically used more as a powerful feature extractor.
Okay, contextual embeddings. That sounds like a big leap. And then came the transformers. This seems like the moment things really took off.
Yeah.
With models like BERT. What was the fundamental shift here?
Oh, absolutely. Transformers and BERT bidirectional encoder representations from transformers in particular, were revolutionary. The core innovation is a mechanism called self-attention.
Self-attention.
Yeah. Unlike the recurrent models like LSTMs that process text sequentially, word by word, self-attention allows the model to weigh the importance of all other words in the input when encoding a specific word, regardless of how far apart they are.
So it can look anywhere in the sentence or even document?
Exactly. It can effectively focus on potentially distant words that are most relevant for understanding the context of a particular word. Think about linking a pronoun like it back to the specific noun it refers to, maybe several sentences earlier. Transformers excel at that. BERT took this attention mechanism and used it in a really clever training setup. It's trained simultaneously on two self-supervised tasks where the labels come from the data itself, no human annotation needed.
Self-supervised, okay.
One is the masked language model, where it has to predict randomly hidden or masked words in a sentence. The other is next sentence prediction, where it looks at two sentences and predicts if the second one logically follows the first. This forces it to learn not just word meanings, but also sentence structure and relationships between sentences. Really deep understanding.
And how does it work structurally? Just high level?
High level, okay. Input text gets broken into tokens, which are often subwords. Each token gets an embedding that combines information about the token itself, its position in the sentence, and which sentence it belongs to, if there are two. These combined embeddings are then fed through multiple layers of transformer encoder blocks. The heart of these blocks is the multi-head attention layer.
Multi-head attention.
Yeah. The intuition is that it allows the model to look at the relationships between words from different perspectives, or heads, simultaneously. It generates multiple kinds of neighborhood embeddings for each token by looking at different combinations of queries, keys, and values derived from the input. It's complex, but incredibly powerful.
So comparing ELMo and BERT then?
The key difference is architecture and how they see context. ELMo uses RNNs, processing sequentially, left to right and right to left. BERT uses transformers, looking at the whole context simultaneously. This makes BERT generally better, especially at capturing those long-range dependencies, and often more computationally efficient to train.
And BERT paved the way for models like GPT-2, right?
Absolutely. The GPT family and many other modern large language models are built directly on this transformer architecture pioneered by models like BERT. It really set a new standard.
Okay, fascinating journey for text. Now, let's switch gears to images. How do we take a picture which is fundamentally just a grid of pixel values, right, and turn that into a powerful, usable feature?
Right, from words to pixels. A really influential model here is ResNet-50. When it came out, it was a breakthrough deep learning model for image classification, achieving, state-of-the-art results on major benchmarks like ImageNet. Its central innovation, the thing that made it work so well, was the use of skip connections, sometimes called residual connections. It introduces this idea of partial linearity.
Skip connections. What problem were they solving?
They were addressing a really critical problem and training very deep neural networks, the vanishing gradients problem.
Ah, right, where the signal gets lost in deep networks.
Exactly. As you backpropagate the error signal through many, many layers, the gradients can become incredibly small, effectively stopping the earlier layers from learning anything useful. ResNet introduced these direct connections that skip over one or more convolutional layers. This creates a shorter path for the gradient to flow, allowing researchers to successfully train much, much deeper networks. ResNet-50 has 50 layers, and there are versions with over 100 without running into this optimization roadblock. Deeper networks often mean better representations.
So the skip connections enable deeper learning. How do we get the embeddings out of ResNet-50 then? Are we just using the final classification?
Usually not, no. In many applications, especially when we're using it for feature extraction, like in our pricing example, we're not actually interested in ResNet-50's final prediction, like, is this a cat or a dog? Instead, we tap into the network before the final classification layer. We extract the activations, the feature representations from one of the deeper hidden layers, often the layer right before the final classification output.
I see.
These activations serve as our image embeddings. They represent a rich, distilled summary of the visual content learned by the network during its original training, often on that huge ImageNet dataset. So for the pricing example, you'd feed the product image into a pre-trained ResNet-50 and pull out the vector from that final hidden layer to use as your image features.
Okay, let's tie this back to the real world then. This isn't just about cool algorithms. How are these powerful embedding techniques actually solving problems? You mentioned hedonic pricing earlier.
Right, exactly. A key application is in hedonic price models. There's some great empirical work cited in the chapter by Bajari and colleagues. Their specific application was predicting the prices of apparel clothes bought and sold on Amazon.com, and they used only the product's image in its text description.
Just the image and text, no other features.
Primarily just those, yeah. The model structure is quite elegant. It takes these high-dimensional inputs, the text and the image features. It then uses BERT for the text and ResNet 50 for the images to convert them into these lower-dimensional value embeddings. And crucially, as we discussed, these BERT and ResNet 50 models were typically pre-trained on those general auxiliary tasks, language modeling, image classification, not specifically on predicting apparel prices.
They brought general world knowledge.
Yeah. Exactly. These robust general-purpose embeddings were then combined, often just concatenated, and fed into another deep neural network. This final network was specifically designed to predict the hedonic prices, often simultaneously across different time periods. That combined value embedding effectively captures the latent or hidden attributes of the product that drive its price.
And how well did it work?
The results were really quite striking. This deep learning approach using embeddings achieved an impressive R-squared of about 90% on the test sample for price prediction.
90%, that's huge.
It really is. And compare that to other methods they tested. If you use the same embeddings but fed them into, say, random forests, the R-squared was around 80%. If you use linear models with embeddings, maybe 70%.
Still decent, but not 90.
Right. And if you went back to using just simple catalog features like brand, category, maybe basic specs without the text and image embeddings, and used a linear model, the R-squared dropped below 40%.
Wow. Okay, that clearly shows the power of these embeddings, especially with complex data and nonlinear models.
Absolutely. It demonstrates how embeddings, particularly when combined with flexible models like neural networks and large data sets, can dramatically improve predictive accuracy. And beyond just prediction, these hedonic prices are super important economically. They're vital for constructing things like cost of living indices, like the Consumer Price Index. They let us put a price on individual product attributes and track how those values change.
That's prediction covered powerfully. But you also mentioned causal inference. How do embeddings help us move beyond just what will happen to understanding why teasing out cause and effect?
This is where things get really exciting, I think, because good prediction is often necessary for good causal inference, especially when dealing with potential confounding variables. Let's revisit that example of price elasticity for toy cars we might have touched on before. In previous work, people used increasingly flexible machine learning methods, going from simple OLS to lasso, then to more complex nonlinear regression to estimate how demand changes with price.
Right, trying to control for confounders better.
Exactly. And as the methods got more flexible, the estimated elasticity became more negative, closer to what economic theory would suggest, implying they were doing a better job controlling for things that affect both price and sales. But those earlier models only use structured data categorical features, numeric features. The really cool new development is incorporating the rich text data from the toy car product descriptions using BERT embeddings directly into the causal analysis framework.
Adding the unstructured text information to the causal model.
Precisely. So by plugging BERT-based predictors for price and for sales into neural networks, and then applying a framework like double machine learning or DML.
DML, okay. That helps isolate the causal effect.
Right. When they did this, the cross-validated R-squared for predicting price jumped up to 0.55, and for predicting sales, it went to 0.027, both surpassing what they got with the previous nonlinear methods that didn't use text, and the resulting point estimate for the price elasticity was managed at 0.174. With a pretty tight 95% confidence interval, managed 0.214, managed 0.135.
So even more negative than before.
Yes, a further increase in the magnitude, and this strongly suggests that by including the rich information captured in the text embeddings, they were able to control for even more observed confounders things described in the text that influence both price and demand. This pushes the elasticity estimate potentially even closer to the true underlying causal effect. It's a powerful demonstration of using embeddings for better causal inference.
Okay, so wrapping this up, what's the big takeaway here? If you're listening to this, what does this all mean? It seems like embeddings are fundamentally changing how we handle complex data.
I think that's right. We've seen how embeddings offer this really revolutionary way to transform the vast, complex, often messy world of unstructured data, your text, your images, into quantifiable, usable numerical features.
Creating a bridge, almost.
Exactly. It's a bridge that allows us to unlock powerful insights and build predictive and, crucially, causal models that were honestly pretty much unimaginable just, a decade or so ago. They effectively close that gap between the rich, nuanced information that actually exists in the world and the structured demands of our advanced analytical methods. It's really opening up new frontiers.
So, given how powerfully these embeddings can reveal hidden patterns, how they turn previously unquantifiable information into measurable insights, here's something to think about. What other vast, complex data sets out there might now be unlocked? Think about fields like, say, art history, analyzing paintings, or cultural studies, looking at vast text archives, maybe even trying to understand the nuances of human emotion captured in videos or audio. Could embeddings open these areas to entirely new forms of analysis, pushing the boundaries of what we can discover about our world? Something to mull over.